In this video for section 8.1, we're going to introduce the idea of a confidence interval. So we're going to start by thinking about this problem. We have an energy drink company, and they sell the drink in 12-ounce bottles. A manager in the quality control lab selects a random sample of 100 bottles and measures the volume of liquid in each. The sample mean is 12.79 ounces. Assume that sigma, the standard deviation, is known to be 0.2 ounces. So this value of 12.79 is, we could say, a best guess for the population mean. Can we measure the volume of every single bottle? Probably not, because then we wouldn't have any bottles left to sell. So instead we're taking a sample and finding the sample mean. So 12.79 is our best guess, or we could also call it a point estimate, which means that it's a single point that we estimate to be the value of the fill amount of each bottle. If we select a different random sample of a different set of 100 bottles and find their mean fill amount, would we expect it to still be 12.79? Probably not exactly. There is variation between samples, and we talked about this earlier. This is called sampling error, and the term sampling error is a little bit misleading because error makes it sound like it's a mistake that you're making, and it's not a mistake. It's a natural phenomenon that occurs just because we're taking different samples, and we're going to get slightly different values. So we might get 12.6, or we might get 12.85. We're probably going to get slightly different values and not exactly 12.79 each time. So instead of relying on a single value to estimate the population mean, we might like to report a range of values that most likely includes the population mean, or whatever parameter we're estimating. This is known as a confidence interval. So you can see in this image the point estimate is in the exact middle of the interval. And then we have a lower limit and an upper limit. When we create confidence intervals, we have a confidence level. The most common ones used are 90%, 95%, and 99%, with 95% probably being the most common out of those. As the confidence level decreases, the interval gets smaller or more narrow. So you might think, well, I would always rather be 99% confident than 90% confident. But the trade-off with that is that if you increase your confidence, you get a wider interval, or in other words, there are more possible values for your true parameter or your true mean. So in the example above, we can use Minitab to find the 95% confidence interval estimate of the fill amount. And if we calculate that out, this is what we get. We always report our intervals in parentheses, again with the lower limit first and then the upper limit, so 12.75 to 12.83 ounces. This indicates that the machine is most likely overfilling the bottles, because it's very unlikely that the true population mean is 12 ounces. Since the lower limit of our interval is 12.75, and the interval does not contain the number 12, we can be pretty confident that the true mean of all the bottles is not 12. So this image here helps us to understand how we interpret a 95% confidence interval. If we were to select many different random samples of 100 bottles, and we were to construct confidence intervals for each of those samples, 95% of those intervals would contain the true population mean. So this says proportion on the side, but this green line could also be the mean. And you can see here, these intervals are most of them all capturing that mean, or the green line goes through most of the intervals. The exception is this one. So 19 of the 20 contain the true population mean, one of them does not. We don't know which one that we ended up with, so we don't really know if it contains the true population mean or not. But 95% of them will contain the true population mean. Now, this next part is really important when you're actually doing the problems in Minitab, and it's that when we create confidence intervals, we need to pay attention to whether the population standard deviation is known, or if we are using a standard deviation estimated from a sample. So if the population standard deviation is known, then the calculation is based on the normal distribution, and in Minitab this is called Z. So the problem will refer to the standard deviation as population standard deviation or may use the symbol sigma. So if you see population standard deviation or known standard deviation or sigma, that's a clue that you are using Z. If standard deviation is not known, then the calculation is based on what's called the t-distribution, sometimes called student t-distribution, but in Minitab you will just see t. And this means that we have a sample standard deviation, or you may see in the problem the S, which stands for sample standard deviation. So we're going to do some examples here. In this first one, we have administrators at a university who are interested in estimating the average amount students spend on textbooks. They take a random sample of 200 students and find their sample mean of 5,230. Past studies have indicated that the population standard deviation is $500. Find a 90% confidence interval for the population mean. So we're going to highlight some of our important information here. In the problem, we have the sample mean, and we have the population standard deviation, which tells me that I'm going to use Z. And then we also have the confidence interval that we are looking for is 90%. So let's go to Minitab here. I'm going to do a new project to clear out the old one. I'm going to go to Stat. And since I have population standard deviation, I'm using one sample Z. You will see one sample T right below it. I'm going to switch this drop down to summarize data and enter my sample size, sample mean, and known standard deviation. So my sample size here was 200. I didn't highlight that, but I could have. Sample mean 5,230, and my known standard deviation was 500. Then I click on options, and here is where I set the confidence level that the problem is asking for. So this problem was asking for 90% confidence, so I enter 90. 95 is going to be the default, but if it's not 95, you need to change it. Click OK. And here is my confidence interval. So it's going to be written with CI in Minitab, and you can see it here, 5,171.8 to 5,288.2. Again, you would pay attention in MyLab to how the problem wants you to round the numbers. So I will write that. Generally in MyLab, they will put the parentheses here for you, and you will just be typing the numbers in. So 5,171.8 and 5,288. That was 0.2. Yep. Okay, so that's that problem. That means that I'm 90% confident that the true mean of the amount that all students spend on textbooks is somewhere between those two numbers. Second problem here, we're looking at a grocery store and they're interested in difference between the customer bill and the true cost. A sample of 20 transactions is selected. That's my sample size. Sample mean is 77 cents. And standard deviation of $1.19. And again, we want to find that 90% confidence interval. Now this one is a little bit tricky because I don't see the word sample or the word population for my standard deviation. But what I have to look at here is that it's worded that the sample mean is 77 cents and standard deviation of $1.19. I can assume that that standard deviation also comes from that sample data. So if it doesn't strictly say population or known or sigma, and it's worded like this, then this means that this is a sample standard deviation. So I'm going to go back to Minitab here. Now, since I'm using sample standard deviation, that means that I'm going to use one sample T. Again, switch to summarize data. Enter my sample size, sample mean, and standard deviation. Click on options and enter my confidence level. All right, and here are my results. So my confidence interval is between 31 cents and $1.23. So that means I am 90% confident that the true amount for all customers that ever buy something at the grocery store, the true difference between their bill and the true cost of items is somewhere between 31 cents and $1.23.